Okay, welcome back. Just wanted to talk a little bit about Quiz Zero. So Quiz Zero um, is due today, I believe. It's not proctored. There's just a couple of questions on there. It's simply to get students familiar. As I posted in the announcement, it's just for students to get familiar with the system. So you will have the questions on Pearson similar to your homework. The assumption would be that the students are doing some work either on paper or on an electronic device. You upload your answers. You submit your answers on Pearson. It'll give you an automatic grade. And then you scan and upload a PDF of your written work. If it's, and I get these questions often, but it's already there in the syllabus regarding multiple choice or true or false statements or short answer questions, then you don't need to write everything out. You simply write out the problem number or question number, saying it's question number 5. It was true or false, so T/F. If it's multiple choice, it's MC. That's all you need to do. You don't have to write everything out. You don't have to write out the question. You do not have to write out the answer. But if it is a numerical or analytical problem, you have to show your work. So without that, students will not receive credit. So same thing with the homework and same thing with the quizzes. The difference between quizzes and homework is that quizzes are timed and you have only one attempt to do it. All right, let's move on from road line analysis and go into the ideal diode model. Okay, ideal diode model. Everybody remember capacitors and inductors from 201? Remember I said depending on the frequency, we model it as a short circuit, as an open circuit, kind of like a similar concept. Okay. If the diode is on, meaning it's forward bias, and we are applying sufficient voltage to it that it turns on, we can model it as a short circuit, SC. If the diode is off, meaning it's in reverse bias, then we model it as an open circuit. That's it. As simple as that. So this is another analysis technique. It's like a quick and easy analysis if we wished to find the voltage or current anywhere in the circuit. Okay, the quick and easy analysis. So forward bias, the diode is on, we replace it with a short circuit. Reverse bias, replace it with an open circuit. Essentially, we remove it from the circuit itself. So how would we analyze a circuit using these conditions? Well, remember I said circuit analysis 201 is mostly analytical, meaning we have fixed equations. Those equations work for a certain set of temperatures, certain set of parameters, and we simply apply those equations and we obtain an answer. Nonlinear devices like diodes, transistors, the analysis methods are numerical. Numerical means we make a lot of assumptions. There are a lot of models that we use to describe the devices and the circuits. And numerical also means that you first make an assumption and you try to find an answer. You try to find a solution. See if that solution works. If it doesn't, then you try a different assumption or different model or different technique. See if that works. And you keep going until you finally have a result that is satisfactory for your system. Okay, so this is one of those first examples. At the beginning of our analysis, we have a circuit. The circuit has a diode in it, resistors, voltage sources, etc. We don't know whether the diode is on or off, yet we want to analyze it and determine the voltage, the current. So the first step is to make an assumption. Doesn't matter what the assumption is. You simply assume whether it's on or whether it's off. When it's on, we replace it with a short circuit. When it's off, we replace it with a open circuit. All right. So we assume a diode state, on or off. We make the replacement. And then we redraw the circuit. Once you redraw the circuit, all you would have in place of the diode is either a wire or an empty space, empty spot. Your circuit has now changed, but there is no diode in the circuit anymore. It's a bunch of resistors and voltage sources or current sources. So then you go back to 201, analyze the circuit using circuit analysis techniques. You analyze it and you solve for the voltage or current. Then you take the solution and compare it to your initial assumption. Does that make sense? Does it correlate? Right? If the diode is on, then your diode voltage should be 0.6 or less, or 0 volts. If it's off, then it should have a high voltage, meaning the anode should be at a lower potential than the cathode. Does it make sense? Does it match up? If it does, then your solution is valid. If it does not, then it's not valid. Then you go back to step 1 and redo until your solution is valid. So you redo all of the steps in that same order until you find a solution that stays valid. All right, let's take a 10-second pause. Think over that. Let me know if you have any questions. Yes. I will. So the question being asked is about step 4 and what it means. So we'll look at examples in the next slide, and then it'll make more sense. Any other questions? Okay, let's look at this example. Circuit is given in figure number A. Figure number A. We have a voltage source on the left, 2 resistors, and a voltage source on the right. And we have 2 diodes in the middle. Okay, 2 diodes in the middle. Now, are the diodes on or are the diodes off? We don't know. So we begin by making an assumption about the 2 diodes. There is, of course, a 2 by 2 matrix. Actually, it's more than that, obviously. Both diodes can be on or both diodes can be off. One can be on and the other can be off, and one can be off, the other one can be on. So it depends on your assumption. So let's say, and I always like to say, and I use this for 201 also, you can make assumptions which can turn out to be incorrect. Does not mean your solution is incorrect. Okay, it doesn't mean your assumption is wrong. It just means that you assumed it opposite of what it actually is. But it doesn't mean your analysis is incorrect. Okay, so when you first begin, you make an assumption that is based on certain logic and on certain rules. So here we'll apply our logic by looking at the value of the voltage sources. What do we see? We see that there is a higher voltage on the left and lower voltage on the right. Okay, now it's not directly applied to those diodes because there are a lot of other components in the middle. But if I see 10 volts on the left and I see 3 volts on the right, my assumption automatically would be that D1 should be on and D2 should be off. Take a pause, think over that statement. Does that logic make sense? Right, few slides ago I stated, for a diode to be forward bias, it means that the anode is at a higher potential than the cathode. For it to be reverse bias, the cathode is higher than the diode. So if I want to begin, I can assume anything I want. I can assume D1 on, D2 on for my analysis. I can assume D1 off, D2 off, and perform the analysis. But again, if I want to be efficient, if I want to save time and effort, I would use this logic. 10 volts is higher than 3 volts. meaning diode D1 should be on and D2 should be off, right? But obviously I know the answer to this circuit. So what I'm going to do is I'm going to choose the opposite of what it actually is. So which is kind of like a giveaway. But I'm going to choose D1 off and D2 on, and then we'll see what happens after that. So first assumption is that D1 is off and D2 is on. If D1 is off, we replace it with a open circuit, right? Open circuit. So D1 is replaced with a open circuit, and D2 is replaced with a short circuit. So it's now simply voltage sources and a couple of resistors. Take a pause and you think over the rearrangement of the components. Yes.
I will just say that's the condition B.
Sorry, what?
Oh,
sorry.
Condition B. Yeah.
No, it's not part of the table. Let me move that out of the way. And this would simply be an assumption right here. That's just the assumptions. Does the setup make sense? Right, and again, the assumption does not matter. We assumed that D1 is off, D2 is on, and so D1 is replaced with an open circuit, D2 is replaced with a short circuit. So now we have to determine the voltages and currents for those diodes. See if the circuit makes sense. If I now try to find the current flowing through this pathway, which is right here, ID2. ID2 is the current flowing through diode 2. What do we have? A simple circuit of a voltage and a resistor, meaning it is 3 volts divided by 6,000 ohms. Gives me 0.5 milliamps. 0.5 milliamps. Right? 3 divided by 6 gives me half. 1 over 1,000 is 1 milli. 0.5 milliamps. Okay. So current is flowing through there. Maybe my assumption might be correct. Because if diode D2 is on, current should be flowing in that direction, right? Current flows through this direction from minus to plus. Some assumption may be valid. Who knows? 1/2 is valid. Let's look at the second one. What do we see? We have the left side of the circuit. Left side of the circuit is, and I'll draw this out here separately. This is 10 volts. And of course, the bottom node is the same between the two circuits. What is the voltage at this point? What is this voltage? What does that circuit remind you of? Again. So what is the voltage at the output terminals? It's an open circuit. For students who were in my class, you should go back and change your grade for 201. Did I hear murmurings of 10? Yes, it is 10. It's an open circuit, meaning current is no longer flowing. If current is no longer flowing, that means the current through 4K resistor is 0. It means both ends of the resistors are the exact same voltage, meaning this terminal has the same voltage as this terminal, 10 volts. If it's 10 volts there, that means this end of the circuit is at 10 volts. And the right side is 3 volts. 10 volts, actually, wait, I am on the other side, right? So 10 volts and 3 volts. What is the difference between those 2 points? 7. And which point is higher? Anode is higher. If my anode is higher, so let me mark out these points. So this is VD1. And what I stated at the beginning, my assumption was that VD1 is off. If VD1 is off, then my assumption is that the cathode is higher than the anode. But the result of my analysis shows me that because of my assumption, this is at 10 volts and the cathode is at 3 volts, which results in plus 7 volts at the anode, which means the diode is not off. Diode is actually on based on my analysis. So here, let me write it out. Anode is higher than the cathode. This is the result of the analysis based on my assumption at the beginning. Let's take a pause, a longer pause. Think over that. Let me know if you have any questions. Do the steps make sense? Right? So my assumption about D2 is correct, but the assumption about D1 is incorrect. Okay. But that does not mean that I just changed the assumption for D1. It means this entire assumption is incorrect. Okay. Just for this first assumption, it turns out that D2 is indeed on and D1 is off. I mean, D2. My initial assumption was that D1 is off and D2 is on. The results of my analysis stated that D1 is also on and D2 is also on. So that means my entire assumption is incorrect, not just one of those 2 points. Okay, that's what I'm trying to say. So then I have to move on to the next possibility. The next possibility could be that D1 and D2 are both on, or D1 and D2 are both off. But as I stated earlier at the beginning, logic states that if you have 10 volts on the left side of a diode and 3 volts on the right side, let's say I have 10 volts over here and 3 volts over here, my D1 diode should be on, right? My assumption would be that D1 is on. And if I have, again, 3 volts here and 10 volts here, D2 logically should be off. So let's roll with that and let's see what we obtain. Okay. So in the second assumption, since D1 is on and D2 is off, I can calculate ID1. Quick note, if diode is on, meaning it's conducting, current is flowing through the diode. So we find, if your assumption is that the diode is on, we find the diode current. If the assumption is that the diode is off, then we find the diode voltage. Okay. If the diode is on, we find the current. If the diode is off, we find the voltage. So here we find ID1. Let's see. ID1 is simply 10 volts divided by 4,000 ohms. Okay. 1 over 400. 1 over, wait. Oh, 6K, I forgot that. So my circuit is like this. Right? So this is ID1. This is 4K. This is 6K. Because the 3 volts is not connected as part of the circuit, I have 4K and 6K in series. So this is 10,000 ohms. One over 1,000. So the answer is 1 milliamp. I obtained a value for the current. That means 1/2 of my assumption is correct. D1 is on. If the result was that my current is negative or 0, then it would be that D1 is off. But in this case, I assume D1 is on, and I obtained a positive value for the diode current, ID1. That means 1/2 of my assumption is correct. Now we'll find VD2. How many of you remember voltage division? This is the circuit. This midpoint is the minus, and then from 6K, we apply plus 3 volts. That's the battery, right? So battery is going like this. Let me make it bigger. Minus, plus, this is 3 volts. And this terminal right here is basically VD2. I've simply taken the 4K and the 6K resistor, and I've redrawn the circuit like this. Circuit has not changed. I'm just redrawing it in a different way to illustrate a point. So what is the voltage between 4K and 6K? I can find from voltage division. So let me call this as node A, and this as node B. So voltage VAB, voltage at A with reference to B, can be given as a fraction of 10 volts. And since I'm finding the voltage across the 6,000 ohm resistor, it would be 6,000 divided by 10,000. 60,000 divided by 10 gives me 6 volts. So voltage across that 6,000 ohm resistor is 6 volts. And again, here's where the circuit analysis technique comes into the picture. Current from this 10 volt source goes from minus to plus. So it causes a voltage drop in this direction. Because it's 10 volts and 10,000 ohms, it's easy to see. It's 4 volts and 6 volts, 4 and 6 with a plus up top and minus at the bottom. It gives me 6 volts. That means VD2 is minus 6 volts. The measurement of VD2 is positive. Sorry, it's not 6 volts, it's 3 volts. It's minus 6 plus 3, which results in minus 3 volts. And that minus is with reference to the diode voltage assumption with this polarity. At the beginning of my analysis, assumption is that diode D2 is off. If diode D2 is off, it means diode D2 is off, right? Which means the cathode is higher than the anode. Okay, do not be confused with a plus and minus signs. That plus and minus signs refers to the diode voltage. It always refers to the anode as positive with reference to the cathode. This is a common point of confusion. Okay, a plus and a minus sign for a diode is always showing the reference of the anode with the reference to the cathode. Okay, you're stating the anode, position of the anode with reference to the cathode. If the anode is higher than the cathode, you get a positive diode voltage. If the anode is lower than the cathode, you get a negative diode voltage, which we obtain in this case. My VD2 is minus 3 volts. It simply means my anode, actually, let me put this as the cathode. So if my right hand is the cathode, anode is plus 3 volts, meaning it's above, or if it's below in this case, minus 3 volts is below. And if it's below, that voltage is negative. Because VD2 is negative, my assumption is correct. Diode is off. Assumption is correct. So both parts of my assumption are correct. D1 was on. I obtained a positive value for the diode current, meaning diode D1 is on. D2 assumption was that D2 is off. I did obtain a negative value for VD2. So my second part of the assumption is also correct, meaning this is correct. Assumption number 2 is correct. Let's take a longer pause. Think over that. Let me know if you have any questions. Any questions at all? Do the steps make sense? Right? After the steps, the circuit can change depending on your assumptions. From that point on, it's a linear circuit with linear components, meaning it's a voltage source or a current source with resistors. Then you have to go back to 201. Hence, I have the homework number 1 as, what is it, homework number 1 or 0? No, it's homework number 1. It's EE201 refresher. Basically, everything that we learned in 201 is in there. And the entire homework is for extra credit. Okay? Entire homework is for extra credit. So the first few problems are with resistive circuit analysis, then it's mesh current and node voltage. But the whole point of that homework is so that students can refresh their knowledge about the circuit analysis. And the exact analysis that we do will be different depending on the circuit. Okay. Then we get to another different kind of model, which is the offset diode model. And I just want to quickly point it out because this is more realistic. Sorry, this is more realistic compared to the ideal diode model. Ideal diode model, we do not include the voltage that is required to turn on the diode. Remember, I mean, the whole point of doing these models, I mean, the analyzing using these different kinds of models is so that you can analyze a circuit like in real life, right? But in real life, you don't have ideal diodes. You would need 0.6 volts of voltage to turn on the diode. So depending on the diode that you're using, and mostly you'd encounter silicon diodes in real life, silicon diodes will turn on at 0.6 volts. And so we introduce a voltage in series with the diode that is required to turn it on. Okay. So we need to offset that voltage, and hence the name or the term offset diode model. So it includes the forward voltage as an offset. Because once you turn on the diode, the voltage across the diode will consume 0.6 volts. If you are taking the lab, you will be able to see that in the first lab itself, okay, which is this Friday. So the forward voltage drop for a silicon diode is 0.6 volts. For a germanium diode is 0.2 volts. Okay, so some amount of a supply voltage is consumed by the diode to turn on, hence the offset diode model. There would not be any difference in the analysis except that you'd have to insert that 0.6 volts in there. That would be the only difference. Okay, then we come to one of the most important equations for a diode PN junction, is the Shockley equation. Shockley is named after William Shockley. There were these three researchers at, I want to say Bell Labs, who invented the first, I will not say invented, but they created a device that was the first operating version of a solid state transistor. Okay, that is still in a museum. That device is still displayed in a museum. And they won the Nobel Prize in Physics in 1965 for the creation of this device. Yes. Sorry, what?
Do they actually use the piece in the museum, or is it?
No. It's just displayed. That's all. It's not used anymore. And I think it was not silicon. I believe they used germanium wire to display that working principle of a transistor. So the names were, let's see, Walter Brattain, Bardeen, and William Shockley. Three of those working together. I think one of them was the boss. The other two were like co-workers or subordinates. And then they actually had a falling out, but they had to come back and receive the Nobel Prize together. The history goes that they had a falling out. One of them left. I can't remember who it was. So one of them left and did not want to share the Nobel Prize. It's like, I deserve it alone. But they said, if we're not going to give it to you alone. If you want, it's all three of you or none of you. And so they had to not kind of like mend, patch up or whatever, but they just got together just to receive the Nobel Prize in 1965. Anyway, so the Shockley equation, that's where the name comes from. It describes the forward diode current. The diode current ID is given by IS times e raised to the term -1. And I'll explain that term, VD over NVT. Okay, so let's take a look at it first. ID, of course, is the diode current. VD is the diode voltage. Okay, ID and VD are the diode voltage and current. IS is the saturation current. It typically is in the picoamps or the femtoamps range. So 10 raised to -12, 10 raised to -15 range. Very small, very, very small. N is an emission coefficient. Typically, it's just 1. Typically, it's just 1. But depending on the application, a manufacturer will provide you a value of that emission coefficient. Could be anywhere between 1 and 2. Typically, at room temperature devices, we simply take it as 1. Okay. So the emission coefficient and the saturation current, you can typically get from the manufacturer because it is part of the manufacturing process. Q is the electron charge. K is the Boltzmann's constant. Both of these are constants. T is the temperature in Kelvin. So if you say room temperature as, 27 degrees C, then it will be 300 Kelvin. Okay. Anyway, T is the temperature in Kelvin. VT is the thermal voltage given by KT over Q. KT over Q. And this is how we can apply the diodes to use the diode as a digital thermometer. or not as a, but you can use diode circuit as a digital thermometer because the diode voltage or the diode current has a very linear relationship to the temperature. There was a question. Yes. Yes, VT right here. This VT is given by this equation, which is the thermal voltage. And that has a very linear relationship with temperature. So digital thermometers, modern digital thermometers, all use a simple diode circuit where the change in temperature changes the diode characteristics, right? It changes the diode voltage and the diode current, and that change is quantified as temperature. This equation, as famous and as good as this model is only valid for a certain set of conditions. Okay. And I again go back to the beginning where I say numerical methods, right? We cannot describe a device or a circuit or a system completely with just one model. Okay. So while this equation is valid for most conditions, it ignores a lot of other things also. If we wish to describe a diode completely, we would need probably like 40 or 50 different terms. Okay. If you think back to Monday and I said, describe yourself in one word, it would be hard to do so because it would not completely describe you as a person, but it is valid nonetheless. One word could describe you, one word could describe me, but it's not a complete description. 2 words, a better description. 50 words, an even better description. Similarly, if you have more terms, you can describe a diode or a device or a system more accurately. So again, while this equation is very famous, it's just one of the models that we can use to describe the diode. Then I want to talk about, everyone remember this, peak voltages, peak-to-peak voltages, and magnitude, VM. So for those of you who were in my class, 201, that M stands for magnitude. Hopefully you remember it. Maybe you don't. Magnitude or amplitude or peak voltage basically tells you what the maximum value of the quantity is on the y-axis. Okay, it's the y-axis values. So in our book and on Pearson system, you might see VM or IM. If you're looking at a different textbook, a different author, a different professor, a different instructor, you might see VP or IP, peak value. They both mean exactly the same thing. It's describing the maximum value or the minimum value on the y-axis. Okay. And then peak to peak is basically both peaks from the positive to the negative. This is important, especially if you're a working engineer and you use an oscilloscope. The values on there would be in peak to peak or peak. Okay, so whether you're taking the lab or you're not taking the lab, on an oscilloscope, when you look at the information for a sine wave, a time varying periodic waveform, you would see peak values VP or VP-P. Okay. So who can describe the RMS value of a waveform? Anyone? That perked you up. 201, remember RMS? RMS. Anyone? And that's the acronym. Yeah, that's the full form of the acronym. Yes, but what does it mean? If you take this area and you take this area and you add it up, what is the average value of the waveform? 0, right? 0. So if you wish to describe a value that could produce a certain amount of energy in a resistor, that would be 0. But mathematically, it's not, I mean, mathematically it would be 0, but real life, it's not 0. An AC waveform goes through a circuit. It is transferring electrical energy to that circuit components, to the resistor. It is transferring electrical energy and converting into thermal energy. Energy is still being transferred. How do we mathematically quantify that? So they decided early on that instead of taking the average value, what we will do is we will square the value first. So if you have a value or a quantity, you have a voltage, you would square the value. Then you would take the average or the mean. And because you took the square at the beginning, now you take the square root. Hence, root of the mean of the square of the quantity. Root means square. That's where it comes from, RMS. For a sinusoidal waveform, it comes out to be 0.707 of your peak value. Think of it in this terms. You have a sine wave. Think of it as a mountain of dirt. And then you flatten it out. That would be the RMS value of the waveform. Okay. For a sine wave only, it is 0.707 times V peak. But then there is also something known as the average value. And what is that average value? That average value is if you simply sum up the area under this curve. 1/2 cycle. Just 1/2 cycle. And that is the average value of that waveform. It's basically integrating. So mathematically, you would say we are integrating the area under the curve. You're summing, excuse me, you're summing up the area under the curve, which means integrating from 0 to pi. One time period, right? Sorry, 1/2 cycle. 2 full cycles, 360 degrees, 0 to 360, 0 to 2 pi. 1/2 cycle is 0 to pi. So you integrate or you sum up from 0 to pi for a sinusoidal waveform, that would give you value of 2 over pi, which comes out to be 0.637. 0.637. Okay. The difference between RMS and average is very, very small. Realistically speaking, I would explain RMS as the value that would dissipate the same amount of thermal energy in a resistor as an equivalent DC source. It has to do with power. Okay, so RMS value is basically how much power is being transferred to a resistor for a AC versus DC. That would be the equivalent AC value. Now, the reason we also speak about V average also has to do with power, but for us, it's simply just look at it in mathematical terms. Simply averaging out 1/2 cycle. You're not looking at a negative half cycle, because if you average out the positive and negative, then that value would be 0. So if you integrate from 0 to 2 pi, the answer would be 0. Make sense? Right? So the average value is you're integrating for 1/2 cycle. If you average from 0 to 2 pi, then the answer would be 0. And then from that point, we'll look at diode circuits. So we'll end class here today, and we'll pick up again here on Friday with the other diode circuits. If you have any questions, I'll be in my office later this afternoon. I will be out of the office for about 15 minutes. I am on campus. I just have to go somewhere for about 15, 20 minutes, and then I'll be back. This would be around between 1:30 and 2 o'clock. Approximately. So I might leave my office around 1:40 and I'll be back shortly after 2 o'clock. And then I'll be there till like 4 or 5 o'clock.